Thank you everyone for joining. We shall begin the lecture as soon as Professor Weissing joins us. He is having some problems, so please give us 2 minutes. I think Sir has joined.
Hello, I think now I'm audible.
Okay, so good evening everyone. I would like to welcome you all to the first online lecture organized by Structural Steel Education Forum. And today's talk on earthquake in India and role of steel structures will be delivered by Professor Yogendra Singh, and it is indeed a privilege to have him with us. Professor Yogendra Singh is currently serving as the Indian Railway Bridge Chair Professor at IIT Roorkee. His research interests include performance-based design of buildings and bridges, seismic vulnerability and risk evaluation, nonlinear modeling and analysis, seismic evaluation and retrofitting of structures, and earthquake engineering in hilly regions. He has more than 28 years of research and teaching experience, has guided 14 Ph.Ds, and has published more than 80 research articles in international journals of repute. He has been a member of several expert teams and code committees, including convener BIS WG-54 on performance-based seismic design of structures, IRC 9.3, 9.4, and 2.4. He has provided consulting services for the structural design of several important buildings, bridges, and dam projects. And before we begin, I would like to request all the participants to leave their questions in the chat box. And after the talk is over, Professor Yogendra Singh will answer them. Sir, we are good to go. I hand over the stage to you to begin the talk.
Thank you, Devyani. There is some echo in my system. I don't know why. I will first switch off my mobile. So let me try with another microphone. Is it better now? Are you able to hear me, Devyani?
Yes, sir, we're able to hear you, sir.
Okay, so now echo is not there. Okay, good. So let me share my screen. Minimize this. I hope my screen is visible now, huh? And it is in presentation mode.
Yes, sir, it is.
It is coming at the top. I think it will go away after some time. Okay. So, good afternoon. We are talking today about earthquakes in India and role of steel structures. So actually, there are two topics here. First, I will talk about earthquakes, the origin of earthquakes, why we are getting earthquakes in India. And then in the second half, we will talk about steel structures. So mostly we have been dealing with RCC structures or masonry structures in India. Steel structures are not that common if we are not talking about industrial structures and bridges. So in buildings, mostly we are dealing with RCC and masonry. So I will talk few salient features of steel structures which make them different from RCC structures, and which way steel structures are having advantages or limitations above the conventional RCC and masonry structures. So let's first talk about earthquakes. So the origin of earthquakes lies in the structure of the earth. So we can earth, it's not that at the top we have a very thin solid layer which we call earth crust, and we are using this crust for all our purposes, including petroleum exploration. Everything lies in this earth crust, and the analogy you can derive with that of an egg, where a very thin shell is there at the top. So relatively our earth crust is also of similar thickness. Then below that we have molten material, magma, and then as we move towards core, the structure changes. But this top structure of the earth, this is important to us, and this leads to earthquakes. And what happens below this solid crystal earth, there is molten material, hot molten material. The temperature towards the core of the earth increase, and because of that there are convection currents. Those convection currents are applying forces on this earth crust in different directions, and due to that this earth crust is broken into different parts, and those parts are moving with respect to each other. And you may ask that what is the proof for that? So the proof for that is in terms of continental drift theory. So what the scientists have observed, that all the landmass of earth which we see today can fit into one single landmass. So it is the hypothesis is that once upon a time, some 225 million years ago, whole of the landmass was together, but because of these convection currents which are there inside the earth structure, that landmass got broken into different plates, and those plates started moving with respect to each other. And you can locate India somewhere here in this. Let me change this to pointer. So you can see that India is somewhere here, and with time it started moving, and after some 135 years ago we were somewhere here, and then we moved further, and this landmass, this plate, which later developed itself into Indo-Australian plate. This was moving towards Eurasian plate, and finally this is the situation currently we have. We can see that the lower part of India, below the Himalayas, that has come from another plate, whereas the top part, which is coming from the Chinese side, that has come from Eurasian plate. So currently India and Australia are at the same plate, and that plate is moving towards Eurasian plate, the Chinese side, and we are losing some around 2 inches per year of the land. So what is happening, this Indo-Australian plate, which is moving towards Eurasian plate, this is going below the Eurasian plate, and slowly it is getting consumed, it gets molten, and there is a lot of force developing at the interface, and as a result of that force, the height of the Himalayas is increasing. So you may be aware that the height of the Everest is actually increasing with a small amount every year. And as a result of that, we are also losing our land to a small amount of 2 inches per year. You may ask that again, what is the proof that this has all really happened? The proof is finding of sea creature fossils in the Himalayas. So in Himalayas, some fossils have been found which belong to the sea creatures. And the reason for that is that this portion between Indian and Eurasian plate, which was sometime called as Tethys Sea, so due to this hitting of these two plates, this portion, which was earlier the seabed, this has lifted up and that has actually formed the Himalayas. And the Himalayas are also called the youngest mountains because this phenomena is the youngest in terms of geological times. I mean, when we consider in terms of years, it is several million years ago, but compared to geological times from the formation of Earth, this is relatively recent phenomena, and it is having problems. One problem is that because the Himalayas are formed of sea deposits which were there at the bed of the Tethys Sea, so due to metamorphism of those sediments, these Himalayan rocks have formed. So these Himalayan rocks are very weak, very fragile. Slopes are very vulnerable to landslides, and then this energy is getting stored continuously at this interface of the two plates. So that energy time and again gets relieved in the form of different earthquakes. So this area is seismically very active, but it's not that earthquakes are occurring only along this boundary. So if we look at the different plates, tectonic plates, which are currently existing on the Earth's surface, so the measurements, these boundaries have been identified as shown here, and different types of motions are occurring at different boundaries. Here you see this triangle notation at the boundaries. This is showing convergent boundaries. So at this location, the plates are moving towards each other. So what we see here in the Himalayas and the northern side of the India, here also we see the convergent boundaries. Then at other locations, the plates are moving away from each other. So there are divergent boundaries. So at divergent boundaries, generally these divergent boundaries fortunately are occurring below the sea. So new earth, new crust is getting created. So there are mid-oceanic ridges which have been found under the deep oceans, and which is the proof that the earth and through the measurement of the magnetic orientations there, it has been found that those ridges have been created at different instants of time, and that shows that how the earth crusts have moved, or these plates at these locations have moved away from each other. And then another type of activity you see, which is shown here. So this plate, Indo-Australian plate, which was one plate, actually it is trying to break into two. So what you see here, this red hedged portion, this is being subjected to very large stresses. And in this region, close to Indonesia and Sumatra, here a lot of energy at the moment is getting dissipated. And we have seen that large earthquakes in the recent past have also occurred here. So this is the current situation. The most seismic part is this circum-Pacific ring. We also call it ring of fire, starting from the western coast of US right up to Japan. So this is the most seismic region, and most of the earthquakes are occurring here, all the western coast of America. Then the northern part of India, this is also quite seismic. So we are having most of the earthquakes here. So if I show you the location of different earthquakes which have been recorded in the past, so most of the earthquakes you see are occurring, largest number of earthquakes are occurring along this Pacific ring of fire. And then in this region also, you see a lot of earthquakes have been recorded in the past. So northern Indian region, this is subjected to earthquakes. These are called interplate earthquakes. So interplate earthquakes are occurring at the boundary of different tectonic plates. And earthquakes are not limited to the boundaries. Those are occurring within the boundaries. Also, you can see that within this Indo-Australian plate also, the earthquakes are occurring. These are called intraplate earthquakes, but generally the intensity of intraplate earthquakes is less as compared to interplate earthquakes. So this color is showing the intensity of those earthquakes, or rather magnitude of those earthquakes. You can see that larger magnitude earthquakes are occurring at the boundaries, or what we call interplate earthquakes. Now, if we see the closure of India, so you can see that most of the earthquakes are occurring in the northern part, but this portion of India here near the Gujarat Kutch area, here also a lot of earthquakes are occurring. So these regions from the beginning have been in the highest seismic zone. So currently this seismic zone we denote as seismic zone 5. So if you look at the current seismic map, seismic zonation map of India, so zone 5 is there near Gujarat, Kutch area, and in the Himalayan region. We have the most seismic zone. So earthquakes, when we try to quantify their energy released, so two terms are oftenly used. One is the magnitude. So magnitude is like the intensity, the total amount of energy released, and intensity is the amount of energy per unit area received at a particular site. So magnitude, we can have analogy with the wattage of the wall, and intensity, we can have the amount of the light in terms of candela we are getting at a distance. So we can see a larger magnitude earthquake at a given distance will cause larger intensity. At the same time, the intensity at a larger distance from a given magnitude earthquake will be smaller, because whatever energy is emitted from an earthquake, that energy gets attenuated. So it gets distributed into larger volume. As the distance increases, it is distributed into a larger volume of earth crust. That's why it reduces per unit area, and also it gets attenuated. The energy gets dissipated as the waves are moving from epicenter or from hypocenter towards the site. In the path, it is when it is traveling through rock and soil, that energy gets dissipated. So due to that, the intensity with distance goes on reducing, whereas magnitude for a given earthquake remains constant. So whether an earthquake is occurring in India or in US, the magnitude will remain same, but its intensity will change from place to place depending on where is the epicenter and how far that particular place is from the epicenter of the earthquake. So these two terms are very common, and these are commonly mistaken also, because many times we hear, especially on TV, that the intensity of earthquake is 6 or 7 on Richter scale. So that is wrong. Intensity is not measured on Richter scale. Magnitude is measured on Richter scale. Intensity is actually the damage potential, which varies, and there are two types of measurement scales available for intensity. One is based on the damage, the quantum of damage which is observed, which we also call subjective scales. So modified Mercalli scale or MSK scale or EMS scale, European macroseismic intensity scale. These are subjective scales which do not require any instrument. It is based on the human observation of the damage. So naturally it is subjected to subjectivity. On the other hand, we can have instrumented intensity scale where we are measuring the intensity in terms of some measurable quantity, which can be measured using some instrument. And those quantities are acceleration and velocity. So how much acceleration is occurring at a particular site or a velocity is occurring, that we can use to define the intensity. So the modern ways, the intensity is defined in terms of either PGA or PGV, or in terms of the response spectrum itself. So what we call spectral acceleration or spectral velocity. So earthquakes have been occurring on Earth's surface from its beginning, and since the mankind started understanding or observing the earthquakes. they have been observing that earthquake causes a lot of damage. Now, why this is causing a lot of damage? This took us some time to understand. And what we understood about earthquakes was that earthquake causes a horizontal force, whereas gravity, which is always acting on our structures, that is acting in vertical direction. So our structures are inherently weaker in horizontal direction. So we know now that acceleration due to gravity, which is acting in vertical direction, which is equal to 1g, is much more than the acceleration which will be usually caused by an earthquake. So in some cases, the acceleration caused due to earthquake in horizontal direction can be close to 1g, but in most of the cases, it is much less than 1g. But still, even if it is less than 1g, it is causing a lot of damage. And the reason for that is that it is horizontal. Now we also know that earthquake does not cause only horizontal force, it also causes vertical force. In fact, earthquake causes acceleration in all the 6 directions. It is not only causing translation, it is causing rotational motion also at any point or any site. Most of our instruments which we are using so far are not able to measure the angular acceleration. That's why most of the times we are talking about the translational components, 2 horizontal and 1 vertical component. Out of those translational components also, the horizontal components are more damaging. So this was the first understanding about earthquake, that it is causing horizontal force. And naturally, after that, the remedy was that we should design our structures for horizontal force. And question was that how much that horizontal force should be. So that value varied something close to 10 to 20%. And it was considered at that time that if we design our structures for 10 to 20% of their weight in the horizontal direction, the structure will be able to survive. As the measurement of earthquake was done, it was seen that the acceleration may vary. So this is our oldest code, the first edition of IS 1893. Some of you might have already seen. So IS 1893, 1962. So at that time, the country was divided into 7 zones, from zone 0 to zone 6. And later on, it was found that there is nothing like zone 0, where earthquakes cannot come. Whole of the country is subjected to seismicity or effect of earthquakes. So zone 0 was done away. Later on, zone 1 was merged into zone 2. And currently what we have is there are 4 zones, but it is starting from zone 2. So zone 2 to zone 5 we have. Zone 1, historically, it has been merged into zone 2, but we are still counting it like this. So we have 4 zones, and zone 2 to zone 5. So when the measurements were made for the earthquake, it was found that actual amplitude of earthquake acceleration is much more than 10% or 20%, which we were using in design of our structures. And those structures which have been designed for 10 to 20% have survived earthquakes in the past. So it was found that even for those structures which were designed for 10 to 20%, those are able to survive earthquake, whereas the actual acceleration during earthquake may be much larger. And what we see here is the record of a very famous earthquake, El Centro earthquake. So the top one is the record of the acceleration, which we obtained from an accelegraph. So accelegraph is the instrument, and it records acceleration. And that acceleration record we call accelerogram. So the top one is the accelerogram. And for El Centro earthquake recorded at this particular site, this acceleration is 0.319 g. Then the velocity, that is the second graph, second plot. So this is plot of the velocity. This can be obtained directly from a seismograph. So seismograph measures the velocity. Or it can also be obtained by integrating the acceleration record obtained from accelegraph. Then the last bottom one is the plot of the displacement. So displacement cannot be measured directly. It is obtained from integration of velocity, which can be either directly measured or that can be obtained by double integration of the accelerogram. So record of accelerogram. So this is the nature of vibration of ground below any structure. And what we see here is that the acceleration is reversing its direction within a fraction of a second. So that is very important. That makes earthquake different than all other types of load. Gravity acting vertically downward throughout the life of the structure doesn't change its direction. Here, this total duration is roughly 30 seconds. So within 30 seconds, we can see that how many times the acceleration has changed its direction. And as a result, the direction of the force, earthquake force, which is acting on the structure, that is also changing its direction. Because earthquake force is inertia force, and earthquake in reality is not causing any real force on the structure. It is only causing the movement of the ground. And due to this movement of the ground, due to inertia of the structure is not able to follow the ground. That's why it is subjected to a fictitious force, which is earthquake force. So earthquake force is not a real force, but a fictitious. For all practical purposes, this fictitious force is as a real force. So it is inertia force, and inertia force is proportional to acceleration. And we can see if acceleration is changing its direction, then earthquake force is also changing its direction. It is a reversible force which is applied. Now, it will be interesting to compare it with the ground, with the wind forces. So wind is also having fluctuating motion or fluctuating velocity. So here you see the plot of velocity during a wind. So what we see here, that this is also fluctuating. There is a dynamic component in wind also. And this dynamic component can also set our structures to vibrations. So vibration or dynamic effect is important during wind also. But there is a difference between wind and earthquake. What we see here is that the wind velocity is fluctuating about an average value here. So it is fluctuating around an average value, and that average value is not zero. It is a value of velocity, average value of velocity. It is fluctuating, but it is not reversing its direction. Whereas in case of earthquake, we can see that it is reversing its direction. It's reversing its direction in a fraction of a second. And that makes earthquake different. Using this characteristic of earthquake, we can design our structures to take advantage of ductility. Whereas in case of wind, we cannot take advantage of ductility because wind is not going to reverse its direction so frequently. It will take hours or days to reverse the direction of the wind. Whereas in case of earthquake, within a fraction of a second, it is reversing its direction. Now the next question which we faced was that earthquake is a reversible force. We can take advantage of that. And taking advantage of that, we can design our structures for only 10 to 20% of its weight in the horizontal direction, and still it can survive the earthquake. But different earthquakes which were recorded had very different characteristics. So here you see the accelerogram of different earthquakes. These accelerographs are like signatures of those earthquakes. And each accelerogram is different than the other accelerogram. So whatever accelerogram we are having, we have recorded in the past, those are unique. And we can extend this that in future, whatever earthquakes we will be recording or which earthquake will be affecting my structure, that will be different than all the earthquakes which have been recorded in the past. Then the question is which earthquake I should consider for design of my structure. So that we have to understand the characteristics of these accelerograms. So different ground motions, these have different characteristics, and these characteristics can be classified into in terms of three parameters. So the first parameter is the amplitude of the ground motion. So amplitude of the ground motion, here these earthquakes have been plotted on the same scale, and the ordinate in the vertical direction is showing the amplitude. So we can see that amplitude is varying, but all these earthquakes are very damaging earthquakes. These are known earthquakes for causing a lot of damage. So one major reason for that damage was their amplitude. So their amplitude is large, so that will cause more damage. So amplitude of an earthquake, which can be depending on whether we have a record of an acceleration, velocity, or displacement, we can call it peak ground acceleration, peak ground velocity, or peak ground displacement. That is one parameter which governs the damage potential of the earthquake. But very interesting observation we can have here regarding this last earthquake. This is Mexico City earthquake. So Mexico City earthquake, it has very low amplitude. So it is plotted on the same scale, so you can compare and see that the amplitude is very, very small. Still, this earthquake caused a lot of damage in Mexico City. And the reason for that was that it is taking too long a time in reversing its direction or frequency content. So it is having very low frequency content as compared to other earthquakes, which are having much higher frequency content. So due to this low frequency, it had a quasi-resonance like situation. It is not a harmonic motion. Earthquake doesn't cause a harmonic motion of the ground, but it has a predominant frequency, and that predominant frequency, when it coincides or it is close to the frequency of the structure, then there is a quasi-resonant like situation. And when the structure is subjected to that quasi-resonant situation, its amplitude goes on increasing, and there is a lot of damage. So that was the reason. So frequency content is also very important to identify the damage potential of an earthquake. The third component, which is still not understood or not used in our design codes, is the duration of the earthquake. So when a structure is subjected to, whether it is steel structure or RCC structure, when it is subjected to earthquake, under each pulse of this earthquake ground motion, so we can consider here that each earthquake time history consists of several pulses, and each pulse will cause some disturbance to our structure. The structure will undergo some deformation, and generally that deformation is more than its yield capacity, and due to that there is some damage, and this damage is cumulative. It gets on accumulating with the successive cycles. So we know that repeated load can cause damage to structures even if it is less than the yield capacity of the structure. So we know fatigue. So when a train or a vehicle is moving over a bridge for millions of cycles, so although the stresses are much less than the yield stress, those are working stresses, but still those are causing some tiny damage, and that damage goes on accumulating, and finally the bridge collapses due to fatigue. Now in case of earthquake, there is repeated loading, but that loading is more than the yield capacity of the structure, and due to that there is permanent displacement, yield displacement, and inelastic displacement, and due to that inelastic displacement there is damage. Under each cycle of loading there is damage to the structure, and that goes on accumulating, and due to that accumulation of the damage, the structure collapses. So we have to keep in mind the duration of the structure also. Currently our codes do not take into account the duration. Those take into account the amplitude and the frequency content, and the amplitude and frequency content together can be represented by response spectrum. So a response spectrum we can understand like this, that we have a series of single degree freedom systems. So single degree freedom systems are simple structures. We can visualize them like single story structures, so which are having one direction of movement. So when those are subjected to, such simple structures are subjected to the same earthquake motion, their response is different. And if we note down the peak response of each of these single degree freedom system and plot them with respect to frequency or the period, the plot is called response spectrum. So here is an example. Two single degree freedom systems. One is having period of 0.5 seconds Another is having a period of 1 second, and a third one is also there that is having a period of 2 seconds. And their damping is 0, 2%. So when these are subjected to the given earthquake of El Centro, we can see that the amplitude of this single degree freedom system, which is having period of 0.5 second, this is 2.67 inch. In case of 1 second, it increases to 5.97, and in case of 2 second period, we can see it is much higher, 7.47 second. And when we consider different amounts of damping, then also we can see that for zero damping, if we are considering undamped system, the response is much larger. And as we increase the damping to 2% and 5%, the response goes on decreasing. So response of a single degree freedom system subjected to the same earthquake will depend on its period and damping. So if we consider a constant damping for all single degree freedom systems here, and we consider their increasing period. So here the mass and the height of the single degree freedom system goes on increasing. That means that the period goes on increasing. So when we are plotting their peak responses with respect to their period for a given amount of damping is considered to be constant in all these single degree freedom systems. Then this plot we call response spectrum. Now when we plot the response for a given earthquake, it is quite zigzag. So we can see here, and then the response, again, it can be any response quantity. It can be displacement of the single degree freedom system. It can be velocity, or it can be acceleration. So what we see at the top, this is the displacement response spectrum. This is the velocity response spectrum, and similarly, we can have acceleration response spectrum. So the shape of the response spectrum, you can see it is somewhat familiar. In the initial portion, very small range, it is constant, then it is increasing, then again it becomes more or less constant, then it starts, this reduces. This reduces very steeply. So for a single earthquake, this is quite zigzag. We do not get a smooth pattern. So what is done in the courts that they consider the normalized shape for a number of earthquakes. And a quantity which is used as response quantity to plot the response spectrum is generally pseudo acceleration. So this pseudo acceleration is different than the real acceleration of the single degree freedom system, although its value is close. If the damping is small, then the value of the pseudo acceleration and the real acceleration is close. But theoretically, both are different. So pseudo acceleration is nothing but omega square times d. So where omega is the angular frequency and d is the displacement. So d is the real displacement. So we measure or note down from analysis the displacement, the peak displacement of the single degree freedom system, multiply it by the corresponding value of omega square, and omega is 2 pi by t. So this becomes t square by 4 pi square. So we get spectral acceleration as displacement into 4 pi by t square, or the displacement in terms of pseudo acceleration. It can be related as a t square by 4 pi square. So we actually measure the displacement, not the acceleration, and we plot pseudo acceleration. Why we do that? Because if we measure the real acceleration of the single degree freedom system, the real acceleration multiplied by mass will give us the inertia force. But actually, we are not interested in the inertia force. We are interested in the forces occurring in our structural members, or what we call stiffness force. So stiffness force depends upon the stiffness and the displacement, whatever deformation is occurring in our members. So that multiplied by the stiffness of that member will give us the force. So we are more interested in the displacement. And displacement is actually expressed in terms of pseudo acceleration. The advantage of expressing it in terms of pseudo acceleration is that when we multiply it by mass, we get directly the force. So it is obtained in a way similar to inertia force, but it is not inertia force, it is stiffness force, and it is the stiffness force which we require for design, not the inertia force. Similarly, we can calculate pseudo velocity also, which is nothing but omega times d. And because the units of the pseudo acceleration and pseudo velocity are same as that of the acceleration and velocity, and their behavior is also similar in the sense that when we multiply pseudo acceleration with mass, it gives us force, but that force is not inertia force. That force is the stiffness force or the forces occurring in the members. So that's why it is very important to us, because we require the stiffness force or the member force for designing our structures, not the inertia force. So that's why pseudo acceleration is more common than the real acceleration. And whatever response spectra we found in codes, those are invariably representing pseudo acceleration, not the real acceleration. But as I told, if the damping is small, 0 to 5%, then the difference between the real acceleration and the pseudo acceleration is not much. And pseudo acceleration itself can be treated as the real acceleration. So as I said, that for individual earthquakes, the shape of the response spectrum, whether it is displacement spectrum or pseudo acceleration spectrum, it is very zigzag. So what the codes do, those consider the spectral shapes, normalized spectral shapes of different earthquakes. And for normalization of that shape, this value here, which is corresponding to zero period. So practically zero period is not possible. Zero period means an infinitely rigid structure. So such a structure is not there. But any structure which is having frequency greater than 33 hertz, or the period is 1 upon 33 seconds, 0.03 seconds, that we consider as infinitely rigid. And the acceleration of that structure, which is having such high stiffness or such short period, that we call zero period. And the corresponding value of this pseudo acceleration we call effective peak ground acceleration or zero period acceleration. So this value of zero period acceleration or effective peak ground acceleration, this is very important. So we can think that this structure will have this type of period, very short period, or the frequency greater than 33 hertz. It will be like a rigid concrete block embedded into soil. So when it is going to move, it will move along with the ground. So its acceleration will be close to that of the ground. Only thing is that it will do some sort of averaging on that acceleration. So that's why this effective peak ground acceleration is like an averaged peak ground acceleration over several points. So this is close to peak ground acceleration, but it is not exactly equal to peak ground acceleration. And that's why we call it effective peak ground acceleration. And this is the most commonly used parameter to define the intensity of earthquakes, this effective peak ground acceleration. And what is given in our code as zone factor Z, that is also this zero period acceleration or effective peak ground acceleration. So what the codes do, they normalize this shape with respect to this effective peak ground acceleration. So this value becomes 1, and then the spectral shape is obtained. Now this spectral shape has 4 distinct ranges. So the first range, which starts from 0 to T naught, we see that here the spectral acceleration is increasing. So that small flat portion here that we are ignoring. So we are starting from zero period and up to this T naught. T naught is close to 0.1 second. In our code, it is 0.1 second. So the acceleration is increasing. Then the acceleration is constant. This range we call acceleration control or acceleration sensitive range, where acceleration is constant. Then we are having this range, which we call velocity control range. Actually, the pseudo velocity here is constant. If I plot the pseudo velocity spectrum by multiplying this by t by 2 pi, so we can understand that this will become constant, but because it is proportional to 1 upon t, and when I multiply t by 2 pi, t will cancel out, so this portion will become constant. And beyond this TL is called long period corner period. So long period corner period of the response spectrum, this is the junction point of the velocity control range and the displacement control range. In the displacement control range or displacement sensitive range of the response spectrum, the spectral acceleration or pseudo acceleration is proportional to 1 upon t square. So this is some constant divided by t square. So it is inversely proportional to 1 upon t square. And you can understand that when I will convert this into acceleration, I have to multiply it by t square by 4 pi square. So t square will cancel out and it will become constant. The shape of the displacement response spectrum will be something like this. So here what you see that in the initial range, the displacement is increasing parabolically and parabolically in the initial range. Then it becomes linear. In the velocity control range, the displacement is increasing linearly. And in the acceleration control range, in the displacement control range, in the long period, the displacement becomes constant. So it becomes a constant displacement range. We also call it displacement sensitive or displacement controlled range. So there is a difference in the shape of the response spectrum for acceleration and displacement. In acceleration, you can see that for periods greater than this TS, and TS varies from 0.4 second to 0.7 second. So for longer periods, the acceleration reduces with the period. The acceleration is reducing and the forces acting on our structure are reducing because forces are mass into acceleration in this case. So those are reducing, but the displacement is not reducing. Displacement continuously increases. So this difference in the shape of the acceleration response spectrum and the displacement response spectrum we have to keep in mind. Now this is the shape of the response spectrum given in our code. It is proportional to 1 upon t up to 4 seconds. Okay, and beyond that, it is assumed to be constant. So now you can see this beyond 4 seconds, when we assume it to be constant, this is not correct. Actually, it should be proportional to 1 upon t square. And when we are assuming it to be constant, it may not be having big problem when we are designing the structure for the forces, because the forces in any case are much smaller because the acceleration is small. But when we are calculating displacements, so displacement will come out to be much higher, because when we assume it to be proportional to 1 upon t square, then the displacement was constant. When we assume it to be proportional to 1 upon t, then this was increasing linearly. But when we assume it constant, this will be increasing parabolically. So the displacement will increase very drastically if we are following this shape of the response spectrum. The shape of the response spectrum has been changed in the revised code, which is under wide circulation. I will talk about that slightly later. Now we take advantage of this shape of the response spectrum. So we can see that this acceleration response spectrum or the spectral acceleration is reducing drastically with period. It is proportional to 1 upon t. And we take advantage of this in base isolation by using period shift. So by using some technique, if we increase the period of the structure, then we can see that as we increase the period from, let us say, 0.5 second to 2 second, so when it is 0.5 second, then this value is reduced when we move to 2 second by roughly 1/4. If it is 1.8 here it is less than 0.6. So in our code, it will change from 2.5 to 0.5, so 1/5 it will reduce. So we take advantage of the shape of the response spectrum in base isolation, and we take advantage of damping in our structures when we are using supplemental energy dissipation devices, because I told that the response depends not only on period, but it also depends on the damping. And as we increase the damping, so even if the period is kept constant, there is no change in the period, but if we increase the damping, the response will go on decreasing. So different types of damping devices are there, which are either based on friction or yielding or viscoelastic deformations or viscosity of the fluid. So different types of dampers are there. Today I will not talk about that because that is a different topic, but we can take advantage of that for increasing the damping. Now, this is the response spectrum which is proposed in our future code, which is going to come in few months, and currently it is in wide circulation. So you can see that the shape of the response spectrum has been corrected here. So up to 6 seconds, it has been considered as velocity control range. It is proportional to 1 upon t. Beyond 6 seconds, it has been made proportional to 1 upon t square. So the displacement control range from 6 seconds to 10 seconds has been recognized in our revised code. Now the other issue regarding quantification of the intensity of the earthquake is related with its return period. Because earthquake is a rare phenomena, so more frequent earthquakes are occurring or repeating themselves more frequently, but larger earthquakes, fortunately, are repeating after a longer time. And this phenomena is random. It varies from place to place, fault to fault, and site to site. So while doing or assessing a hazard corresponding to design for our structure, two approaches are available. One is what we call deterministic seismic hazard assessment, and another is probabilistic seismic hazard assessment. In deterministic seismic hazard assessment, we consider what maximum earthquake is possible at a site. So we consider all the faults in the vicinity of that site. When I say vicinity, it is considered as about 300 kilometers radius. So within 300 kilometer radius, we consider all the faults, all those faults which can generate earthquakes, which have a potential to generate earthquake. And then we identify what magnitude that earthquake can be caused at that fault. And based on the magnitude, what type of earthquake it will occur, whether it is normal fault or reverse fault or strike slip fault or oblique fault. So considering those characteristics of the fault and the magnitude which it can generate, using attenuation relationships. These attenuation relationships are nothing but these are regression relationships obtained from the past earthquakes. So whatever past earthquakes have been recorded, these functions are fitted, equations are fitted, and using those equations, we can predict what earthquake intensity we are expecting, what amplitude or even frequency content we are going to expect at our site. So this method is called deterministic seismic hazard assessment. This gives us a unique value of seismic hazard. Now, when we are using regression relationships, then there also there is a variance. So we can consider the median or average value, or we can consider median plus the standard deviation. So conventionally, in our code, what we are currently using is the median value, which is obtained from the fault, which is having the maximum magnitude potential, using attenuation relationship, and median value of that attenuation relationship is used. Currently, that is the methodology followed in our code. On the other hand, in probabilistic seismic hazard assessment, we do not depend only on the maximum earthquake causing fault. We consider the contribution of all the faults. So maybe a particular fault is not contributing that much in the maximum intensity which will occur, but at the lower intensity earthquakes which can occur at that site, those faults may also be contributing. So along with the potential magnitude, we also consider the likelihood of those earthquakes occurring. So we also consider the probability of occurrence. And considering the probability of occurrence, we get the hazard in terms of PGA or PGV or any other terms, and a corresponding probability of accidents. So this is additional information which we get as compared to DSHA. So using PSHA, we don't get only the intensity, we also get a corresponding probability. And based on that probability, the earthquake levels are defined, and these earthquake levels, commonly used earthquake levels, I have shown in this table. So this can be anything like 50% probability of accidents in 50 years to 2% probability of occurrence in, or 2% probability of accidents in 50 years. This 2% in 50 years, 50 years here is representing the average design life of a structure, a common structure, a building. So that corresponds to a return period of 2,475 years, roughly 2,500 years. So this is the most commonly notation used in the codes, which we call maximum considered earthquakes, MCE. Then another one, which is very commonly used, is this 10% probability of accidents in 50 years, which corresponds to a return period of 475 years. We call it design basis earthquake. And interestingly, this is the earthquake which we have been using in design. So it is interesting to note here that when we are designing our structures, our intention is that our structure should be able to survive this MC, the maximum considered earthquake. But we are not designing for MC, we're designing for DB. And the relationship between DB and MC is not constant. It varies from place to place. And in American code, they are using this relationship between DB and MC as 1.5. So MC they are considering as 1.5 times DB. In our code, we are considering MC as 2 times the DB. So we consider MC as 2 times DB. Now here it is important to understand that the zone factor Z, which is given in our code, what is that representing? So as I said that the Z, the zone factor is representing zero period acceleration, which is nothing but effective peak ground acceleration. And it is the median value of EPGA, which is obtained from DSHA, deterministic seismic hazard assessment. So currently the zonation and the zone factor, which are given in our code, are based on DSHA. And these are the median values. So median value of JAT, deterministic seismic hazard assessment actually is not giving any return period. So there is no concept of DB and MC there. But after we have this probabilistic seismic hazard assessment and these terms MC and DB have come into being. So there is an attempt to compare this. So how we can compare this JAD value, which is given in our code, with MC or DV, which are the concept of PSHA. So if we look at ASC7, the current code provides a comparison between DSHA and PSHA, and it says that when we are performing DSHA, then we can consider median plus 1 sigma, that is 84 percentile. So 84 percentile value which we are getting from DSHA, that can be considered as MC. So what is given in our code is actually not 84 percentile, it is 50 percentile. So that is the median value. So to compare it with the MC, we have to go for the historical development in ASC7. So when we look at ASC7 versions prior to 2005, so there we see that the MC is defined as 1.5 times the median value obtained from DSHA. So same is existing in our code also. So actually the MC as per our code is 1.5 times JAD. And this 1.5 factor is appearing as a load factor. And that's why it is causing some confusion among the designers. So the designers think that it is a load factor, but in case of earthquake, actually there is not a load factor. So this 1.5 factor, which is given in our code as load factor, is actually a correction factor from median value to 84 percentile value, which can be treated as MC. So when we multiply this by 1.5 JAD, this JAD we multiplied by 1.5, then it becomes MC. And as I said that the relationship between MC and DB is assumed to be 2 in our code. So when we multiply this, or rather we divide this 1.5 JAD by 2, it becomes DB. So that's why in our design, we are using 1.5 JAD by 2. So JAD by 2 we consider while calculating AH as JAD by 2 IYR into SAYG. And 1.5 we are using later when we are converting this from median to 8 percentile. And JAD by 2 without multiplication by 1.5, that is representing serviceability level earthquake. So serviceability level earthquake having roughly 50% probability of occurrence in 50 years, that is used for working stress design. So in working stress design or serviceability limit state checks, we are using this ZY2. So if we have to develop the design response spectra in our code corresponding to DV and MC. So we have to understand that what is given in our code as SAYG is actually not response spectrum. It is normalized spectral shape. So a better way of representing that will be SAYZ. So actually it is SAYZ. And when we multiply it by 1.5Z, then it becomes MC. And when we multiply it by 0.75Z, that is 1.5Z by 2, then it becomes DV. And when we multiply it by 0.5Z, then it becomes serviceability level earthquakes. So these three multiplication factor we are using in our code to convert this into serviceability, design basis, and maximum considered earthquake. Our code does not say anything about what we are expecting from our building or structure when we are designing using this DV. It doesn't say anything, but it is understood that if we are designing as per this, then our structure will be able to survive the maximum considered earthquake without collapse. It doesn't mean that it will not damage, it will get damaged, but hopefully it will not collapse. But that is also not guaranteed in the code. Code does not have any mechanism to guarantee that. So this is the current seismic zonation map, which consists of 4 zones, zone 2 to zone 5. And the most severe zone, zone 5, is there in the Himalayas and in the Kutch region. These are the corresponding zone factors Z. So these zone factors Z are nothing but the value of effective peak ground acceleration EPGA or ZPA corresponding to the median values which are obtained from DSHA, deterministic seismic hazard assessment. And we have to convert this into DV and MC. We have to multiply by the corresponding factors. On the other hand, this new code which is under revision and in wide circulation, it is expected to come in a few months. So here now, this concept has been changed. It is based on probabilistic seismic hazard assessment. And for different structures, the design return period is defined. So for which return period we will design, that return period has been specified. So there are normal structures, important structures, and critical structures. So normal structures will be designed for 475 years return period as usual, like today when we are designing, although it is based on DSHA, but it is equivalent to 475 years return period, the DB which we are using in our design. Then critical structures, hospitals and other critical buildings, those will be designed for 2500 years, MCE, those will be designed. And in between those important structures, those will be designed for 975 years. So it is not that alarming as it may appear, because at the moment also we are using importance factors. So we use, in case of our hospital buildings or important buildings, we are using an importance factor of 1.5. So that is somewhere in between the DB and MC. So it is not exactly MC, but it is somewhat close to MC. And this is the new zoning map. In new zoning map, there are 5 zones. And these 5 zones are starting from zone 2 to zone 6. Zone 1 is still not there historically, as just to keep that historical development, that zone 1 was merged with zone 2, and there is no zone in country which we can consider as less severe and where we can ignore the earthquake resistant design. So to keep that notion, that feeling, it is starting from zone 2 and it is going up to zone 6. And zone 6 is this middle Himalayan region. So earlier you could see that zone 5 was in the form of patches. Here it is not in the form of patches, but there is a continuous zone here. And a zone 5 here between zone 4 and this is that Indo-Gangetic plain, foothills of Himalayas. So here the zone 5 has been carved out. Other zones are similar, not same, but similar to the previous zones. And this zone factor Z now, it is given for different return periods. So it is given corresponding to MC, 2500 years return period, and it is also given corresponding to other periods, including DBE. So here you can see that the ratio between DB and MCE now, in case of seismic zone 6, the most seismic zone, it is 1.5, whereas as in the lower seismic zones, it is 2. So actually it is varying between 1.5 and 2, as I said earlier, that the relationship between DB and MC is not constant. It varies from place to place between 1.5 and 2. So for higher seismic zones, it is 1.5, and for lower seismic zones, it is the relationship is 2. The ratio between DB and MC is 2. So that's about earthquake. Now I will talk about structures. So how our structures resist earthquake. As I said that we never design our structures for the actual earthquake force, which those will be subjected to during earthquake. We are designing those for much lower earthquake forces. And how do they survive? Even when designed for much lower earthquake force, they survive that by the virtue of their ductility capacity. So this ductility capacity, we can define like this, that if I subject a structure to load and plot the load versus displacement. So when I'm loading it in one direction, initially this loading curve is linear. So we call it linear elastic. If I apply some load on my structure and unload it, I will come back to the original position. This property is called elastic, and the behavior is linear. So we call it linear elastic. But then the yielding occurs, especially in case of steel structures, we can have a distinct yield point. So at the yielding, there is permanent displacement. So without any increase in the force, there is a displacement. And this displacement we call inelastic or plastic displacement. This is permanent displacement. And even if I unload my structure fully, it will not come back to the original position, but there will be some residual permanent displacement or strain. Then there will be the phenomena of strain hardening. And if I start unloading from anywhere here, we can see that it is not going to follow the loading path. The unloading path will be parallel to the loading path in such a way that when I unload it fully here, the stress or the force has become zero. Still, there is a permanent strain or displacement. And if I remove to that, if I want to remove that permanent displacement or strain fully, I have to apply a load in the opposite direction. And then here, with this much force in the opposite direction, the displacement or the strain will become zero. And if I apply the force, if I continue applying force in the opposite direction, this curve will continue. And then when I change the direction again, it will follow a path which is parallel to the original path. So under cyclic behavior, I will get this type of a hoop, quadratic loop I will get here. So this loop is representing the energy dissipated by the structure. So initially when our structure is linear elastic, it is following the same path in loading and unloading. It will come back to the original position. So whatever work I do during loading, same amount of work I get back, same amount of energy I get back when I am unloading it. But here, loading and unloading paths are different when the structure has yielded. And as a result, we can see that the amount of work done while loading is more than the amount of energy I'm getting back during unloading. So some amount of energy has been lost. It has been converted into other forms of energy. This we call the dissipation of the energy. And we can visualize earthquake as if it is imparting energy over structure. And if the structure has to survive, it has to dissipate that energy. So whatever energy has been imparted to our structure, if it is able to dissipate that energy at the same or higher rate, it will be able to survive the earthquake. Otherwise, it will collapse. So size of this hysteretic loop, this becomes important because this is giving us the amount of energy being dissipated by the structure per cycle. So if I look at some experimental curves, this is for structural steel. So for structural steel, we can see that the loading and unloading path is more or less ideal. So we can see the slope of the loading and unloading is parallel. So loading and unloading paths are parallel. So If we compare this with RCC, so here we can see that in case of RCC, the shape of the hysteretic loop has changed, and we get here a reduction in the shape of the hysteretic loop, and this phenomena we call pinching. And due to this, there is dissipation of energy. There is a reduction in the dissipation of energy, and due to that pinching, with the same strength and displacement, my structure is able to dissipate less energy per cycle. Another difference you can see comparing with steel structures, that in steel structures, in successive loading cycles, at the same displacement, we get almost the same force. But here we can see in successive cycles, at the same displacement, the force which we are getting goes on reducing. And the slope of the loading path also goes on reducing. So this is degradation or cyclic degradation of strength and stiffness. So in case of concrete, and when we compare it with masonry here, you can see that this degradation of stiffness and strength is even more visible. So there is reduction in the area of the hysteretic loop, there is reduction in the stiffness, there is reduction in it. So that shows the advantage or the superiority of steel structures. Steel, we know, is a ductile material. On the other hand, concrete and masonry are brittle material. In RCC, we depend on the ductility of steel, reinforcing steel, but still, because we are depending on concrete also, concrete is also resisting the forces. So there is degradation in the stiffness, strength, and the energy dissipation capacity of structures made of RCC and masonry. So it still has its advantage. Now we can take advantage of this ductility by not designing our structures for that force which will occur on an elastic structure. And what we do here, you can see this red curve. This is representing the behavior of a hypothetical structure. A hypothetical structure which is infinitely strong, and because we will never design our structure to have this much strength, that's why we are calling it hypothetical structure. So its low displacement behavior is given by linear behavior, and this is the force on this elastic string, VE, the elastic force, and the corresponding displacement here. This is the elastic delta E, displacement or displacement of the elastic structure. Real structure we will never design for this VE, rather we will design it for much reduced force, VY, only 10 to 20% of this force, which will occur on the elastic structure. So the behavior of the real structure is given by this blue curve. So it will follow the same linear elastic behavior up to Vy, and after that it will become plastic. So this is the behavior of the inelastic structure. Now what is interesting here is that it has been observed during past earthquakes that the maximum displacement of the elastic and inelastic structure is same. So if we analyze our structure for a large number of earthquakes, we see that on an average, the displacement of different structures which have been designed for different strength levels, the maximum displacement is same. So this is equal displacement of principle. Although it does not have any theoretical proof, it is based on the observation. So for most of the structures, it has been found that the amount of energy dissipation due to this cyclic behavior is such that the maximum displacement which we are getting for the elastic and inelastic structure is same. And using geometry, we can show that the ratio of the VE to Vy is same as delta M to delta Y. Ratio of V to Vy we call as the response reduction factor R, and delta M to delta Y we call the ductility ratio. So this R is equal to mu. Response reduction factor is equal to ductility ratio. So this is a very important relationship. Using this relationship, we are currently designing our structures, taking advantage of inelastic energy dissipation. So the advantage of inelastic energy dissipation can be represented by this simple equation that R we can consider equal to mu. Now, what I explained just now, that was valid for long period structures. In case of short period structures, the slightly changes. So in case of short period structures, it has been observed that the maximum displacement is not same, but the energy equivalent area under the two curves, under the elastic curve and the inelastic curve, the maximum energy stored by the two systems is same. And if we use a little bit of geometry, we can get R is equal to square root of 2 mu minus 1. So this is valid for short period structures. Whereas for long period structures, it was equal energy, equal displacement principles. Using both equal displacement principles and equal energy principle, we can analyze or design our structures in a simplified manner like this. So here we try to estimate the hazard as realistically as possible. So this blue curve at the top, this is showing the hazard. So hazard, the blue curve, this is realistic. This is obtained for the site either using DSHA or PSHA. And then we reduce it by the response reduction factor R. And then we design for this course, the design base year. And when we are designing, we are using limit state method. We are using some partial material factors of safety, and we are using characteristic strength. So due to those partial factors of safety and characteristic strength, the actual strength of our structure is slightly higher than what we are using. Not slightly, it is roughly 2 times of that. But still, it is much less than the actual response spectrum, the actual demand. So we are reducing the actual demand. So if we plot this demand response spectrum for MCE, we are reducing it by 2R. So roughly 10 times we are reducing. This redesign is 10% of the elastic base shear, which we will get on our structure. We design it using limit state method, so it becomes 2 times of that, so roughly 20%. But still, it is only 20% of the demand which will be there on the elastic structure. So we are able to take advantage of this because of the energy dissipation. And the response reduction factors through which we can take advantage of this inelastic energy dissipation without going through nonlinear analysis, we can use these response reduction factors. These are defined in the code. Interesting here to see is the steel frames with concentric braces and steel frames with eccentric braces. So what you see here, that the response reduction factor given for concentric braces is 4, whereas for eccentric braces, it is given 5. So eccentric braces are considered to be better from earthquake resistant point of view as compared to concentric braces. I will explain that in successive slides. So when we are designing any structure, we are designing it for vertical load as well as lateral load. And for lateral load resistance, we are providing a structural system that is resisting the lateral force. The simplest structural system which we can provide to resist the lateral forces is pin jointed frame. So pin jointed frame, when the beam is having simple connections with the column, it cannot transfer the moment. So in that case, the columns will act as cantilever. So whatever lateral force is applied, that will be resisted by these columns as cantilever. And the moment which we are going to get at the base, so the speed gets divided into 2. So P by 2 multiplied by the height h. So PH by 2 and PH by 2 will be the moment in the 2 columns for which we have to design our structures. Now I can improve the efficiency of this system by making it rigid jointed. So let's first consider a hypothetical case where the beam is infinitely rigid and the beam column joint is moment connection. So if the beam is infinitely rigid and the connection is moment connection, we can see that our column is going to deform in double curvature and it will remain vertical at top and bottom. Point of counterflexion will be somewhere in between. The moment which will generate here will be PH by 4. So we can see that the moment has been reduced to half. But some reactions have developed in my columns. So one of the column will be subjected to compression, another will be subjected to tension. So part of the load, lateral load, we are not transferring now through bending action. We are transferring that through the axial action. And when we transfer it through the axial action, the efficiency of the system increases. Because any object or any member, whether it is column or brace or beam, it is stronger and stiffer in axial action than in bending action. Now, in a real frame, the beam will not be infinitely rigid. The connection can be moment connection. So in that case, the beam is going to deform, but still the column is bending in double curvature, and the moment which will develop here will be somewhere in between ph/2 and ph/4, and it increases its efficiency because part of the load is transferred through axial action in the columns, and as a result, this becomes a more efficient system. We can make it further efficient system by providing a brace. So when we provide a brace, a diagonal member here, then the bending moment is almost eliminated. There is no bending moment. The force is being transferred through axial action. So this becomes more efficient system. But the problem is that this brace, which is subjected to compression, this will buckle. In linear elastic range, we can take care of that buckling by controlling the slenderness ratio, making our brace stocky. So by controlling the slenderness ratio, we can avoid buckling, but we cannot avoid buckling in the inelastic range. So when this is going to yield, after yielding, its effective modulus of elasticity will become 0. And when the modulus of elasticity will become 0, irrespective of what is the slenderness ratio of this is going to buckle. If I plot the load displacement curve for a moment frame, it is going to be like this. Initially, it will be linear elastic, and then hinges will develop at the ends of the beam and in the columns, and I will get this type of a behavior. We can see that this is showing good ductility, but when I have a brace frame, then this brace frame, the brace is going to be subjected to compressive force. And after yielding, this is going to buckle. And what we see here, that in tension, when this brace is subjected to tension, we get good ductility. But when the brace is subjected to compression, due to buckling, its strength is lost suddenly. So we do not get that good amount of ductility here. And that's why in case of braced frames, the response reduction factor is reduced because it is giving us better strength and stiffness, but it is not giving us good ductility. So in case of earthquake, we depend not only on strength and stiffness, we also depend on ductility. And that's why braced frame is not considered to be an ideal system in case of earthquake. This we can improve by providing eccentric braces, and eccentric braces we provide in such a way that the yielding of the beam beyond the brace occurs in flexion or shear. Interestingly, steel is a material which is very ductile in shear. In fact, it is more ductile in shear than in flexion. RCC, on the other hand, we know is brittle in shear. So in RCC, we have to avoid shear failure mode. But in case of steel structures, we desire the failure to occur in shear because shear is a more ductile mode. So using this concept of increasing efficiency, transferring more and more load through axial action, this is the hierarchy of steel structural systems to reduce lateral loads. So the lowest in this hierarchy is the semi-rigid frame. So in semi-rigid frame, the columns are bending more or less like cantilevers. Those can be used for the lowest heights. Then we have these rigid jointed frames where the efficiency increases. Then we have eccentrically braced frames. So we do not prefer concentrically braced frame. We use eccentrically braced frames. Then we combine eccentrically braced frame with outriggers. So the efficiency of our system increases further. So this eccentrically braced frames with outriggers are nothing but like vertical trusses, a combination of vertical and horizontal trusses, so that more and more load is transferred through axial action than in bending action, and the efficiency increases. Here what we see is that these are the frames in which the columns from, so at the bottom you see the plans of these structural systems. The columns, load resisting columns from the interior of the building have been removed and put along the perimeter. So as we put the lateral load resisting material along the perimeter, the efficiency increases. And what we see here, all the columns have been put along the perimeter, and we have what we call frame tube system. So this is the frame tube system. And frame tube system, it is acting like a hollow tube. This is subjected to a drawback of shear lag. So like our steel sections, those are subjected to shear lag. All flanged and hollow sections are subjected to shear lag. So this is also subjected to shear lag. That shear lag can be overcome to some extent by providing number of valves here. So this is called multi-cell tube. So multiple tubes or a tube having number of valves in each direction. So here the shear lag will be reduced. And the most efficient system is where we combine the effect of the concept of the bracing and the tube. So this is test tube. So in test tube, we have a tube which is also having a vertical truss along with that. So the tallest system in steel can be achieved using this concept of trussed tube, combining the effect of frame tube and the vertical truss. Just to show you some of these photographs of the real buildings. So this is World Trade Center, although this building is no more. This building, the famous Twin Towers, these were the classical examples of frame tubes. So here you can see closely spaced columns, steel columns, which are connected by deep spandrel beams. So it acted like a hollow tube, or you can think of a structure consisting of 4 frames along its perimeter, which were having closely spaced columns and deep beams. Or you can also think of that it was a steel hollow tube which was having punctures for windows. So either way we can visualize it. This is another example, Sears Towers. So here we have multi-cell tube. So 9 cells are there, and different cells are stopped. Those are terminated at different heights. So that gives a peculiar architectural shape to this building. Now, what has been the problem in our steel structures? So during past earthquakes, the failure of the steel structures has been due to buckling. Now, buckling can occur in case of a slender structure. It can occur because of its length. So here on the right side, I show this lateral torsional buckling. So especially when there is an open type of section, so that open type of section will be subjected to buckling even under elastic load. But during earthquake, what happens? The members near the joints, those are subjected to yielding. And when these are yielding, these are subjected to inelastic buckling. So due to inelastic buckling, because the modulus of elasticity here, effective modulus of elasticity reduces to almost 0. So due to that, the buckling occurs close to the joint. And as a result, we are not able to achieve we are not able to take advantage of the full plastic capacity of these members. So this can be controlled by considering adequate thickness of the web and flange. and our code defines the sections, steel sections, into different categories, starting from plastic section to non-compact sections. So the plastic sections are those where this buckling will occur, because in any case we cannot avoid this. After yielding, the buckling is going to occur, but this buckling will be limited to an extent, or it will occur after the plastic moment capacity has been achieved. So when we achieve the plastic moment capacity and then this buckling is occurring, that is the best behavior we can achieve from our steel sections. The other major cause of failure or damage during past earthquakes have been the failure of the joints. So the beam and columns are meeting. At those locations, there is high concentration of these stresses. So at the beam column joint, the bending moment changing its sign. So when the bending moment is changing its sign, very high shear stresses develop. So the joints are subjected to very high shear stresses, and most of the failures have been observed at the joint. So here we have this buckling of the concentric brace. So concentric brace can be subjected to buckling, and when it is subjected to several cycles, reversible cycles of earthquake, in each cycle it will be subjected to buckling, and then it will straighten, and then it will buckle again. So we can have rupture type of failure. So what you see here, buckling and rupture. This photograph is not that good, but very instructive photograph to show what type of damage can be expected in case of concentric braces. This is another set of photographs which is showing the buckling of the concentric braces during earthquake. On the other hand, in case of eccentric braced frames, this phenomena can be avoided. So in eccentric braced frames, what we are doing, braces are connected to the beams in such a way that those are not meeting at the same point. So here we have the single brace. It is connected eccentrically with the column. Here we have these two braces which are connected in such a way that there is a small portion left in between, which we will call link. This is the portion of the beam which will yield during earthquake. So we design it in such a way that the buckling strength of these braces is more than the shear strength or flexile strength of this link portion. Eccentric brace, high ductility is achieved. Response reduction factor of 5 is permitted, but it is not just simply making the braces eccentric. We have to also ensure that the capacity of the braces is protected. That means the braces are having buckling capacity higher than the yielding capacity of this link. So this link will be subjected to either flexural yielding or shear yielding. We prefer shear yielding, as I told that steel sections are more ductile in shear. So we prefer shear yielding, and to avoid shear buckling of the web, you can see that here there are stiffeners provided on the web. So these stiffeners are to protect shear buckling of the web so that we can achieve high ductility in this portion. So we can see that all the yielding and damage is going to occur in this link portion. The braces will not yield. Those are protected using capacity design. So those have been designed to have higher strength than this. And another possibility is that we can make this link portion intentionally weaker. So here in this particular photograph, the link portion consists of the same beam, but we can have another member here, which is of a smaller section. So that member will yield before the buckling of these braces, and energy will be dissipated through that link portion by shear yielding. And even if it gets damaged badly after earthquake, it can be removed and replaced. So this is the most important structure from earthquake point of view. So far, we haven't got much information about its behavior during real earthquake. Only a few damage reports are there, and one such damage report in case of eccentric bracing is this. So here the failure has occurred at the location where the brace is joining the link, because at that location lot of shear is going to develop in the brace. So the bracket has to coincide with the flange of the brace. So there was some eccentricity you can see here, and that eccentricity has caused rupture of the bottom flange of our beam in shear. So the detailing of this junction between this and the link, this is important. You can see here this bracket is exactly coinciding with the flange of the brace. So this detailing here, this becomes important. If there is a little eccentricity, then we can have that very high shear stresses will develop, and that can cause shear failure of our brace. So that's all about steel structures and earthquakes. So thank you very much for joining. If there are questions, I can take up. So
Thank you, sir.
You have track of the questions, so you can read those questions for me, and I will try to answer those.
Yes, sir. So we have one query.
Yeah.
It is response spectrum method is said to be more accurate than equivalent static method. Why still there is clause to scale up the base shear when response spectrum base is lesser than equivalent static?
Okay. So as I said that the shape of the response spectrum is such that it is very sensitive. The force calculated is very sensitive to the period. So if there is a little error in calculation of the period, that will be reflected in our design base shear. And due to some reason, if I'm considering the period which I'm estimating longer than the actual, the forces which I will calculate will be on non-conservative side, on unsafe side. Now, period we are calculating using modeling. In modeling, there are several assumptions, and some of those assumptions may lead to period being longer than the actual. Then the period also depends on the cracking, especially in case of RCC structures. It depends on the cracking of the concrete. So how much amount of cracking is occurring? So initially stiffness of any structure is higher, and as the damage proceeds, the cracking proceeds, it becomes more flexible, the period goes on increasing. So there is a lot of uncertainty about the period which we are calculating from our model. So when we are using response spectrum method or any dynamic analysis method, our analysis procedure is more accurate, but the error in calculation of the period cannot be ruled out. So it may happen that by mistake, we consider a longer period, and that will result in smaller design forces, and our structure will be designed on unconservative side, unsafe side. So to avoid that, the code says that we can use time history analysis or response spectrum analysis, which is dynamic analysis, more accurate. But the base shear should be matched with a period which is given in the code, which is more realistic. That period has been obtained from the measurement of the period on the actual structures. So experimentally measured period. So based on that, the code asks to calculate as the design base shear. So that's why the code is saying that we have to match our or scale our base shear with what we are obtaining using equivalent static method. But here it is not the equivalent static method which the code is having emphasis on. It is the period which is given in the code. So we have to calculate the base shear using the period given in the code, and then whatever method we use, our design base shear should not be lower than that. That's what the code is ensuring. Any other queries there?
No, sir. We received just one query. If anybody else has any query, they can add. If not, then I would like to thank you for your talk, sir. And I would like to thank all the participants who have joined us today. And with this, we can end it.
Okay, thank you. Thank you for this opportunity and this new initiative. I congratulate you and all the organizers of this forum. I think it will go a long way, and we will have more interactive sessions and more sessions with other speakers.
Yes, sir. Yes, sir. Looking forward to having more talks and technical lectures and discussions in future, and creating more awareness on steel structures, their design and fabrication processes. Thank you so much.
Okay, bye-bye.